This is Statistics 243 at Berkeley for Friday, November 21st. Okay, let's go ahead and get started. So there are two main things I wanted to do today. One is to do a demonstration of using the optim function in R, and we'll see some of the options for the optim function. And the other was to work through our way through an example of the EM algorithm and deriving an EM optimization routine for a particular problem. So how many of you have some familiarity with EM? Anybody? Okay, just a couple people. Okay, so I'll start off with the optim example. So the idea is that as you see some of these functions in R, they're using a lot of the techniques that we've already talked about, sort of the actual algorithms and what the algorithms are all about. So if you were to use optimize, that does one-dimensional optimization. You can see it does something that involves golden section search, which we talked about very early on in the unit. And if you're trying to find, I think this is for a one-dimensional function as well. If you want to find the zero function, which we've obviously seen is the same as finding a minimum, in the case where we have a derivative, then you can use uniroot. But the real workhorses in R, because we're often doing multivariate optimization, are optim, and there's a new package, or new function. Did I write that here? Oh, maybe it's at the bottom here. Oh, okay, yeah. There's a new package called OptimX that provides a function called OptimX. And the idea is OptimX is sort of a meta-optimization function that will try a whole bunch of other different optimization functions. So OptimX will actually try some of the methods that are in Optim, and it'll try NLM as well. And so Optim allows you to do Nelder-Mead, which we talked a lot about. It allows you to do BFGS, which we talked about. It allows you to do simulated annealing, and a couple others. And then NLM gives sort of a different variation on a Newton-style method. So there are lots of different options in terms of which one you choose. I think OptimX is kind of a nice thing to use. I'm sort of used to using Optim because OptimX came around after I really started doing much in the way of optimization, and so that's what we're going to see here. Because in particular, it'll show us a few of the particular optimization routines that we've already seen in this unit. And then one other thing to be aware of is that in some cases you can just work out the derivative of your objective function. And if you can do that, it's often a good idea to pass a function that encodes that derivative and calculates that derivative into the optimization routine. And that way it doesn't have to try and calculate numerical derivatives along the way. So if it's not too hard to derive the derivative, that's often and then code that up, that's often a pretty good thing to do. But it's not necessary for any of these things. So any of these things that need derivatives, we'll just calculate numerical derivatives via a finite difference method that we'll talk about in a couple weeks. Okay, so let's just work our way through an example. So the example comes from some research that I'm involved with people up at Lawrence Berkeley Lab. And they're climate scientists, and they're interested in understanding the frequency of extreme weather events. And they're interested in seeing if the frequency of those events and the magnitude of those events is changing over time. So this might be related to climate change, those sorts of questions. So a simple version of this problem is that if this were a histogram of daily rainfall, daily precipitation, over many, many years, say, they might be interested in knowing how does the tail of this distribution behave? Are really, really extreme rainfall days becoming more common? How common are they? If I wanted to know sort of what's the event that we think on average would occur only once every 20 years or once every 100 years, if you fit a distribution to data, you can basically estimate that what I just said. You can estimate that 1 in 100 year, 1 in 50 year event by basically looking at percentiles of the fitted distribution. Okay, so that's sort of the backstory here. So the way, I don't want to go into too many details of where this likelihood comes from, but the idea is that folks have done some theoretical work in thinking about tails of distributions, and it turns out there's some theoretical justification for saying that if I choose some threshold that's fairly high up in the distribution, fairly far to the right in the distribution, and I call that threshold C, that this is a a distribution with 3 parameters in it that should generally hold to characterize the distribution of it. It should characterize the distribution of the tail of the distribution. That's sort of a confusing way to say it. If you just think about the observations to the right of the cutoff, this is a distribution that is generally a good one to fit to just the observations to the right of the cutoff. So you're sort of conditioning on the fact that you're to the right of the cutoff, and then fitting a distribution just to these observations. So if you go ahead and write out the likelihood, it looks something like this. This C is this cutoff here. There's a product here over the x's, the xi's, which are the observations to the right of the cutoff here. And there are 3 parameters. There's sort of a location parameter. It's not quite the mean, but it's sort of, you can think of it as sort of telling us something about where the center of this distribution is for the values in the tail. And there's a sigma that basically just says, for these observations in the tail, how spread out are they? And there's this c parameter, which I have a terrible time writing, which is basically how heavy the tail is. So it basically says how fat the tail is out here. So those are the 3 parameters that we need to estimate if we're going to fit this distribution to these data that are in the right-hand side of this distribution. Okay, so questions about the context? Yeah.
And would you have to be pretty certain that the distribution you're using is a good approximation of the data?
Yeah, in this case, in general, you want to have some idea that the distribution you use that the data could plausibly come from that distribution, could be approximated by that distribution. The statistical theory says that if as I make this cutoff, as I move this cutoff more and more to the right, asymptotically, the distribution of the tail should follow this distribution. And the question is just how far do I have to move this cutoff to the right? And of course, as I move the cutoff to the right, I have fewer and fewer data to make use of. So there's a trade-off here of, as this goes to the right, this distribution should be a good fit, but you don't want to make it too far to the right because I'm not going to make data with which to estimate the parameters. Other questions? All right, so let's actually see this. I'll run Optima in a few different ways here, and we can see this. So these are data that I've converted, so they're daily precipitation in inches, and I'm setting the threshold to be 3 inches in a day, which is fairly extreme rainfall. So here's the original data on the left-hand side. So this is all the data on the left-hand side, all of the precipitation. And you'll notice that most of them are in this bin because most days it doesn't rain at all. So there are lots of days with no rainfall. And if I choose my cutoff to be 3, you'll notice these are all the observations. I can actually count them up. There are 8 plus 4 plus 3 plus 3 plus 2 plus 1. There aren't very many observations out in that tail. So we are in this sparse setting. But the idea is the further out we go in the tail, the better this distribution is as an approximation to the behavior of tails of distributions. So the idea is we're just going to fit the likelihood for this subset of the data, and then we're going to try and see if we can get convergence and get the parameter estimates to see if we can recover the parameter estimates. Okay, so I have, what have I done here? Oh, actually, no. So the bigger than 3 was me just doing some initial plotting. It looks like what I'm actually doing here is choosing the threshold as, if I take all the days on which it rained at all, I'm going to take this cutoff to be the 98th percentile of the days that were at least somewhat wet or rainy. So that's how I'm choosing the threshold. And that threshold then becomes the value. Okay, that is the value 3. So I guess I sort of went back and said, oh, I'll just use 3 for plotting purposes. But the threshold is almost exactly 3. And this is me just coding up my log likelihood. So I'm just taking the log of that likelihood, and I'm just writing that out as R code, and that's the function that I'm going to optimize. And actually, it should be the negative log likelihood so that I can do minimization. Okay, so what do I need to do when I'm doing optimization? I need to choose the optimization method I'm going to use. And what else do I generally need? I need the starting values. Right? So in this case, I'm not going to sort of go through the logic of how I chose these starting values, but based on me having worked with these distributions some before and having some sense of what are realistic parameters and how the data relate to reasonable values of the parameters, I'm coming up with initial values, which are this in1, in2, and for that third parameter, the shape of the distribution, I'm using 0.1. So to some degree, I obtained those from just doing some sort of initial calculations with the data. So those are my initial values, and now I'm going to go ahead and fit this. And by default, if I don't specify the method argument, so you'll notice down here I say method equals BFGS, which we've talked about. If I don't specify the method argument, it should use Nelder-Mead as the default, so that method that doesn't use derivatives. And if you look at the optim function, if you did help on optim, what you'd see is that it wants initial values, it wants a function that evaluates the objective function, and then there's a ... argument that you can pass in additional arguments that get fed into the objective function. So all of these things, the y, the thresh, the npy, are all things that are arguments to my pp.like, which is my negative log likelihood function. And then this control argument is actually an argument for the optim function. And in this case, I'm just saying, give me back some information about the different iterations of as the optimization proceeds. So I can go ahead and run this. Wait, where am I here? Oh, sorry, I'm well far down of where I meant to be. I don't think it changes what I was just saying, but okay. So Nelder-Mead is the default. We'll go ahead and see what happens. So it gives us some idea of how many times it actually evaluated the objective function. If I had passed in a gradient function, which I didn't, it would say how often it had evaluated the gradient function. And it gives me the value of the objective function at the minimum. And it gives me something that's really important to look at to see if it actually converged. So this is basically a code to say whether or not the optimization converged. In this case, 0 means yes, it converged, which is a little bit confusing. But if you see something other than 0, that means something's gone wrong and it hasn't actually converged according to whatever convergence criteria are being used. And then it gives back as the $par. The output of this is a list, as you might have already gathered, and the par element of that list is the parameter value. So this is 1.92. This is the location. This is the scale. And this is that shape parameter. And just for the sake of being able to compare, as we keep moving down and do some other try out optim in some other ways, I just wrote out those MLEs or putative MLEs here. So we don't know for sure that we found a global minimum, but we'll try another few runs of it to see if we think we have. And you can see here that in this trace, it's sort of giving back some information about. I'm not sure why there are two numbers here, but you can see that it would sort of make sense that these are basically the values of the objective function as it goes through the iterations, and you can see these are decreasing down towards whatever it reached as the value at what it thinks is the minimum. And you can also see here it sort of is using the terminology we saw for Nelder-Mead about sort of reflections and expansions and things like that. Although I think maybe it's using somewhat different terms than I used. Okay, so any questions about that usage? Okay, so we could also try a Newton-like method. So we're just going to do the exact same thing. We're going to start at the same starting values, but we're going to use BFGS. And when we see that also gives a convergence code of 0, so that's also reassuring. It says it evaluated the function 43 times. Oh, sorry, I misspoke before. For Nelder-Mead, obviously, we don't use the gradient, so it makes sense it didn't actually evaluate the gradient function at all. I was sort of thinking that in the back of my head that we were thinking about a Newton-like method. So in this case, even though we didn't pass in a gradient function, this must be how many times it tried to calculate numerical gradients, although I would think it would be doing it more than that. So that's a little bit surprising. In any event, it gives us some idea of how many iterations it took. So it says after 10 iterations, it's at this value of the objective function. It actually doesn't seem to say here exactly how many iterations it did, but it said at the final iteration it was at this value of the objective function. And if we look at the parameter estimates, they're basically the same as the ones we got from using Nelder-Mead. They sort of vary in some of the far out decimal places here, but they're for sort of substantive purposes, the two methods have converged to the same place, which is reassuring. And we could play around if we wanted to and see which one took longer. And both in these cases, neither of these took all that long. Although I've actually, in terms of estimating standard errors, I've also played around with using bootstrapping here. And at that point, as you get more data and you do more bootstrap replicates, it becomes more relevant how fast the optimizations are. So that might be something I would be interested in understanding, is which of those was faster, just in terms of computer time. Okay, so another good thing that we've talked about is this idea of starting at multiple starting points to try and avoid the problem that we might have reached a local minimum instead of a global minimum. So it's always good to try at least a few starting values. So in this case, I guess I came up with some other means of coming up with starting values that they're at least somewhat different than the starting values that I already played around with. So I'll just calling this one init1 instead of init0. And I'm just going to redo my optimization with the same call, except just with different starting values. So nothing very complicated here. You can see again, it thinks it converged, and it does seem like it's reaching essentially the same parameter values, but from those different starting places and getting to the same place. And it would be a good idea also to check to see if the value of the objective function seems like it's the same starting at the two starting values, or how close those two values are. And we can do the same thing with BFGS, and again, it looks like it's giving us essentially the same thing. So all of that is fairly reassuring. Okay, so I did want to illustrate a few more things to actually see what happens when things go wrong. So what I'm going to do here is I'm going to choose starting values that I know are kind of crazy starting values. So remember that I don't remember what exactly I started that scale parameter, which is sort of a standard deviation kind of like parameter before, but we know that from having done the initial optimization that the right value maybe is probably around 1.38. So in this case, I'm actually going to start that standard deviation like parameter at 0.01, which is sort of saying that I think the standard deviation, the scaling of this is like this, and in reality the data say the scaling is more like this. So that's a pretty bad starting value in this case. But if I hadn't thought about the problem, I might just have sort of come up with this and proceeded with it, and then this is what would have happened. Why does this keep doing that? Okay, so in this case, I guess I saved this as this object out. So if I look at out, okay. So in this case, if I look at out, so this was with Nelder-Mead, and even with this bad starting value, it actually converged to the same place as all of these other times that I've run this. So I get the 1.92, the 1.38, and the minus 0.20, and it says that, oh, indeed, according to its convergence criteria, I've converged. But if instead I were to run this with those same quote-unquote bad initial values, and the other thing I can do is I can take the inverse of the Hessian. I can take the inverse of the Hessian, or the inverse of this is the Hessian for the negative log likelihood. So the inverse of that Hessian, and this will be the asymptotic covariance matrix for the parameter estimates. So this says if I took the square root of the diagonal values, those would give me the standard errors that go along with these three maximum likelihood estimators. So that's just standard asymptotic theory. But now if I do this using BFGS with that same quote-unquote bad starting value, it says it's converged. The convergence code says, yes, indeed, I've converged. You'll notice a couple things here. One is the parameter estimates. I've got a minus 3.94. I've got a 26. Obviously, 26 is a much wider spread than I was getting for. And I've got this shape parameter of minus 2.5. It turns out because I know something about this distribution, I actually know that minus 2.5 is just a crazy value for that parameter and is not a realistic value in essentially any data set. But even if we didn't know that, another thing that we might see here, well, another thing that we should see here is if I've run a few of these optimizations, this value of 80 is much, we were getting 61 before for the objective function at the quote-unquote minimum. This is obviously not the minimum if I was able to find somewhere else in this parameter space where it's 61 and this is 80. So this this must be a local minimum instead of a global minimum. And the other thing is just in the theme that I've sort of mentioned a few times before, of just keep your eyes open and try and avoid doing anything really stupid. Or if you see something that looks weird, then it probably something is weird. If we find the asymptotic covariance for this particular set of parameter values, that if one thought that this were the minimum, it says that the square root of these values are the standard errors. The square root of this is going to be something like 1 times 10 to the minus 6, which is really, really small. So either we believe that we have really, really, really high precision in estimating this parameter, or something funky has gone on in terms of the optimization. And you'll also notice there's a negative value here, so we're not even going to be able to take a square root of this in terms of trying to come up with a standard error for that, for the middle parameter. So that's another indication that if you get standard errors that you don't believe, something weird may have gone on in the optimization, and maybe you haven't actually converged to the minimum. Okay, so any questions about that?
The algorithm doesn't want to check if it has any negative standard errors?
Well, there's nothing about the optimization function that's going to be doing this inverse of the information matrix and trying to find the standard errors. That's just us doing post-processing. Yeah. So we're just using a black box optimization algorithm that has no idea that we're doing something statistical, and then we're using the Hessian. Yeah. Okay, so another thing that you might imagine is in lots of different problems, the scale of the units of the things that we're measuring could vary wildly. So I transform things so that I have precipitation in inches, but suppose somebody gave me the data and the precipitation was in thousands of inches. In that case, I would get these y's that were 1,000 times larger than the y's that I got before, and similarly, my threshold would be 1,000 times as big. And so I might have done the optimization on this very different scale for the y's, and if I do that, what I'll see is that these parameter values are quite different than these, and it's not just that they're scaled up. Like the location parameter might just be 1,000 times what I got before, and the same thing for the standard deviation parameter, but they're not. They're actually quite different. And this shape parameter should be invariant to the scale of the magnitude of the y's. So this says that just by changing the scale of my observations, I've changed my maximum likelihood estimators, or at least what this optimization thinks are the maximum likelihood estimators. I've changed that quite substantially. And in this case, if I were to run BFGS with these observations on a very different scale, I actually get that it doesn't even report that it's converged. Okay, so this is not all that hard a problem. It's only 3 parameters, but you can see I'm already getting sort of wonky behavior just by virtue of the fact that I've changed the scale of the observations. Okay, so one of the rules of thumb is, there are a couple of rules of thumb. One is, in general, you want the magnitudes of things when you're doing optimization to be around 1. You don't want to have really big values or really, really small values. So one idea is that if you change a parameter 1 unit, that you want your objective function to change roughly 1 unit. And another is that if you change one parameter by 1 unit, that should have more or less the same effect on the objective function as changing another parameter by 1 unit. So it's good to have parameters sort of be on the same scale. And that sort of relates back to what we saw last time when we were talking about contours and about the fact that gradient descent is going to work best if we have circular contours. So if I have contours that look like this when I have parameters theta 1 and theta 2, and all of a sudden if I sort of change the parameterization and make this theta 1 divided by 1,000 or theta 1 times 1,000, you can imagine that now the contours will get sort of stretched in one of the directions. And that's generally, and as we sort of talked about, we generally want to have more sort of circular contours. So a couple of the options in the optim function are basically to do some on-the-fly rescaling of the parameters, and that's what this is going to do. This par scale basically says, hey, the first 2 parameters are now operating on a scale that's 1,000 times as big as the 3rd parameter. And so what optim will do is basically sort of do some inverse scaling of things, such that when it basically divides by 1,000 for both of these 2 dimensions, we're back to the case where basically a unit step in one direction should have roughly the same effect on the objective function as a unit change in one of the other directions. So it's always good to sort of get a sense for if I change my parameter by a little bit, or if I change it by parameter by one, if I change it, different parameters by one, how much of an effect does that have on the objective function? And once I do that, that actually fixes things quite nicely here. You'll notice that this 1920 is just 1,000 times this guy, and that the 1382 is 1,000 times that, and that this shape parameter is now basically the same as it was before. So just doing this rescaling of in terms of the coordinates helped quite a bit in terms of the optimization. Okay. Is there a question? Yeah, Lei.
So in the real case, when we don't know whether the scale is right or not, are you trying to rescale everything to the unit?
In the real case, one thing you could do is just play around with plugging in some different values of the parameters and seeing how the objective function changes as you change the values of the parameters. So you can get sort of a sense for that by just sort of plugging in values and experimenting a little bit. The other thing you can do, which sort of leads into the next thing I was going to say, is you can try and do some plotting if you're in low enough dimensions and see how the objective function changes with the parameters. So here what I'm doing is I've got 3 parameters, so I basically would need to do plotting in 3 dimensions and then show the objective function in the 4th dimension, which is obviously quite hard. But what I'm going to do is I'm basically going to create a series of plots where I have different values for that shape parameter, the 3rd parameter, and then I do a 2-dimensional plotting of the objective function as a function of the location and the scale parameter. So this is basically what I've asked you to do in one of the problems on the problem set. And so I won't go through the details of how I did that. You should be able to follow the R code fairly readily. But once I do that, I think I need the fields package loaded in for this image.plot function. Here's the... So for a few different values of the shape parameter, -0.3, -0.25, -0.2, up through 0.25, I'm plotting how the objective function varies as a function of the location and the scale. And bluer and yellower colors are better because we're trying to find the minimum. So one of the things we can see is that indeed it seems like sort of the best values are down here around 2 or 3 for the location and around maybe 1 or so for the scale, which is sort of consistent with what we saw from the actual optimization. And we can sort of get a sense, I mean it's a little bit hard to tell with this color scale, but if we look more carefully we might be able to get a sense for what's a good value of the shape parameter. So which of these pictures has the lower of the optimum. And then there are a couple of weird things that go on here. So something weird happens when the shape parameter is 0. In this case, the numerical value is very, very close to 0. And I don't think I want to take the time to go into explaining what's going on here. And there's also something weird, another weird thing with this likelihood function, which is actually there's a constraint imposed that it's not valid if for certain parts of the R3. It's not valid for certain combinations of these 3 parameters. And the places where it's not valid are anywhere where you see white here. And so basically what I've done, which is sort of a not great way of doing this, but people will do this for this particular problem, is I've basically set the objective function to be infinity whenever I'm in those parts of the space where the parameters are not valid. So the objective function is not actually differentiable in this case based on the way that I set it up. It turns out it works to still use a Newton-like method as long as you start in a reasonable starting place, but that's why there's this white space here. Okay. Any questions? All right, I think that basically closes off what I want to say about Optim, and let's move on to EM. Yeah. Okay, so I'm gonna come back to the beginning parts of section 8, but I thought it would be good to try and walk through the EM example since you guys have that on your problem set. Okay, so EM is basically a method that was originally people came up with it as a way to maximize the likelihood where you have some missing data. So the idea is that if I had the full data and none of it was missing, I would just be able to do my usual likelihood maximization, and that's what's indicated by well, let's see. So what I want to maximize is the likelihood for theta given the available data that I have. And now I'm going to introduce some notation and say, well, what if the missing data z were actually available to me? Then the complete data would be y, which is x and z combined. And ideally, I would have the complete data, and I would just maximize the likelihood with respect to y. Okay. Well, in general, if you've got missing data, one way you could think about this problem is that you are trying to maximize this likelihood, this distribution of the data given the parameter values, and you're trying to maximize that actually as a function of theta, but you write it down as a data for the density given the parameter values. And one criterion we could use to, well, the way that you would do this, the standard way you would do this, is you would basically write down the joint density for the available data and the missing data, and then you would integrate with respect to the missing data. So you're basically integrating over the uncertainty, sort of integrating over the variability from the missing observations. Because this involves an integral, that is often going to be hard to do in terms of actually doing that integral. But the EM algorithm basically introduces a recipe for us to do this optimization. And what it basically does is, let's see, how do I want to do it? Yeah, I guess I'll say it this way. So what it basically does is it tries to estimate it basically tries to maximize the expected value of the log likelihood given the log likelihood expressed as a function of all of the data, but conditioning on the data that I've actually observed, which are the x's, and also in this case as taking the expected value and basically making use of the current value of the parameters, which are the thetas at the tth iteration. So you compute this expected value. This is basically going to average over the missing z's, and it's just going to be a function of the x's and then of theta, and there are going to be some theta t's in there. And then you're going to go ahead and maximize that with respect to theta, and that's going to give you theta t plus 1. So you basically, the sort of steps are that you compute this expected value, you maximize with respect to theta, that gives you the next theta t. You then compute this expected value with that new theta sub t, and you repeat that process. And the tricky part about, I think the most tricky part about EM, and it sort of trips people up pretty frequently in terms of the notation, is we have both theta t's floating around, which are the current values of the thetas, and we have the theta, the true theta, the parameter thetas that we're maximizing with respect to. And so I think we just need to sort of work through an example, and hopefully that will become more clear. Okay, so the reason it's called EM is there's this E step, which is calculating this expected log likelihood, averaging over the missing data, and then there's an M step, which is maximizing that criterion with respect to theta to get the next value of theta. So one of the cool things about EM is that it doesn't have to be explicitly a missing data problem. Like, it doesn't have to be that you've gone out and collected some data and then you didn't collect some other data and that you explicitly have some missing data. So the idea is that you can often derive an EM algorithm by basically saying, here's the data I have. Suppose that I had some additional information that I could think of as sort of missing information or missing data. If I had that missing data, that would make the problem easier to solve. And if you can sort of couch it in that way, then you can often employ an EM algorithm where the sort of the missingness is stuff that you introduce, or sort of latent variables that you introduce into the problem. So we're going to see an example of that where we in a mixture model where we can sort of think about what are the natural latent variables, what's sort of the natural missing data that if we had it, it would make the problem easier. And when you're thinking about the problem on the problem set, which is this idea of having the censored data, you can think equivalently about what would be the complete data if I had all of the information that I wanted to. And then in this case, I don't have all the information, so I'm going to employ this EM algorithm. Okay, so let's see a mixture model example. So the example we're going to see here is looks like this. So it's basically like what we saw in section for that simulation study problem. So the idea is we might not be able to represent the density for some data as a single normal distribution, for example, but we might if we use enough normal distributions, be able to represent it as a mixture of normal distributions. So that mixture of normal distributions, so I'm just going to assume for what we're going to derive in a minute that these f's are normal distributions. There are parameters phi sub k, which are the mean and standard deviation, or mean and variance of the kth components. So this is going to be mu sub k and sigma sub k. And then there are these pi sub k's, which say what's the proportion of, what's the weight on each of the mixture components. So I'm also going to have a pi sub k. And so the picture is the same as the one we basically saw in section, that you could think of a mixture distribution where I have one component with some weight on it, another component maybe with less weight, and another component that would be a normal distribution, another component that has some weight on it. So the pi 1 is basically the area under this curve, the pi 2 is the area under this curve, the pi 3 is the area under this one, and then the mu's and the k's determine the mean and the spread of those three distributions. Okay, so questions about the setup? Okay, and I'm going to call theta, sorry, there ends up being a ton of notation here, as being the collection of all the pi k's and the collection of all of the phi k's. So in this case, there would be 3 of these, and there would be three sets of these guys, but it depends on how many components we have in our mixture distribution. Okay, so if we think about this problem, we can think about what's the natural latent variable that we can introduce into the problem that sort of makes the problem easier to think about and to derive estimators for. So anybody have an idea of what that is here? Some people may have seen this problem before. What information could I give you that if you knew that information would make it really easy to figure out, to estimate the pi's and to estimate the means and the standard deviations? We have a bunch of observations. So suppose I have x1 up through xn. Yeah. Yeah, so if I knew that x1 came from one of these 3 distributions, right, and then I knew the same thing for x2 up through xn, I'm going to call that z1 up through zn, and those are going to be the membership indicators. Okay. So suppose that I knew, and suppose that I knew that 10 of these observations came from this first component. So 10 observations out of 100. Suppose actually that's a bad example. Suppose I knew that, say, 35 out of the 100 observations came from this first component. How would I go about estimating the pi 1 in this case? It's the obvious estimator of pi 1 if I know the 35 out of the 100 are from the first component. It's just the empirical probability, 0.35. And if I know which of these x's come from this distribution, how would I estimate these 2 parameters? I just find the sample mean, that's the maximum likelihood estimator, and I take the sample standard deviation and multiply by n, and that would be my estimator for the sample variance. That would be my estimator for sigma squared k. So if I knew the z's, then this becomes sort of an easy problem. And then the question is, well, what can I do if I formulated this as, here are my missing data, here are my observed data, let me try and implement EM and see what falls out of doing that. Okay, so let's do a little bit of derivation here. Stop me if you get confused about the notation, because that's sort of, I think, the hardest part of this. So what do I have? Well, I have fx of x given theta. So this would be the distribution. This is the original distribution, and that would be pi 1 times a normal distribution of x given mu 1 and sigma 1. I'm not going to write out the normal density, but imagine that we're here, plus pi 2 of a normal density for x given mu2 and sigma 2, and so on and so forth. And now I can think about, well, what I need for EM is I need to compute, I need to write down the log likelihood for the complete data, for the x's and the z's jointly. Okay, and there's a pair, there's an x and a z for each. There's a pair x and z for each observation. So I basically need to be able to write down this F distribution. So if I think about that for a little bit, it's not too hard to see that the result is going to be that F of x and z as a function of theta. Well, that's just going to be f of x given z and theta. I'm being loose with notation here. You generally don't actually condition on something that's not a random variable, but I think you sort of see what I mean. What's the distribution of this for a given value of theta is basically what I mean there. And here I actually am conditioning because z is a random variable here. And now I've got f of z given theta. So this is just writing down the marginal and the conditional distribution to get the joint distribution for x and z together. And in this particular problem, what's that going to look like? That's going to be the x given z. If you tell me what z is, well, one way of writing that that's going to be convenient is I'm going to sum over the different components of the mixture, and I'm going to say the indicator that z equals k. So if the observation is from the kth class, then I'm going to have my normal distribution for, well, I think I want to write this as, I'm going to go back to writing this as f sub k of x sub I given mu sub k and sigma sub k. So this is only going to be non-zero for the case where z is equal to k. So just using the indicator function. So that is this f of x given z and theta. If you tell me z, this is the density for x. It's just the picking out the normal distribution that's relevant for x because I know it's from that component. What's the marginal distribution for z? I guess, sorry, I'm using my notation here is a little bit bad. I need i's here because I had i's in the pieces over here. What's my marginal distribution for z? Well, if I sort of think of averaging over the x's, those are just the pi's. Those are just the probability of being in any given component. So that's just going to be pi sub k. So you can think of this as this is the probability that zi equals k. If I don't know what the value of x is, and I just want to know what's the probability that z falls in any one of the components, that's just going to be the marginal pi's. Okay. All right. So now we can start following the EM recipe. I now have the log likelihood for the complete data because I have the x's and the z's, and that was what I defined y to be. I need to take the log of this. So if I were thinking about this as over all the observations, then I would have a product over all the observations. So this becomes a product from I up through 1 to n. And now I'm going to take a log of this whole thing. And so this is going to be the sum over I of the log of this business here. So I'm gonna have the log of this plus the log of pi k. And then there's a little bit of a trick here, which is that usually you'd think, well, taking the log of a sum is going to be hard. Like, you can't make that any simpler, right? Just have the log of the sum. But in this case, I know that the only one of these that's non-zero is the one where, for when zi is equal, for the k, when z is indicating that I'm in the kth class. So this is just going to end up being the indicator that zi equals k times the log of fk of xi. Am I missing events? And I would still have my sum over k here. Okay, so sort of move the indicator outside the log just because it works out nicely in this case. Let's see. Oh, actually, so if I'm thinking about this sum of, I got messed up with where the pi k was. So this is a sum over, let's see what's going on here. So sum over k. So log of the product is the sum of the logs, and that's the log of this whole thing. That's the log of pi k. For some reason, in my notes I had this indicator also being over here, but it doesn't seem to be right now that I look at it. All right, well, let's proceed. I'm actually not going to finish the derivation today anyway. Okay, so now the key thing is I now have my log likelihood for the complete data, and I need to take the expected value. Okay. So the key thing to realize here is I'm going to take an expected value of this. And this is going to be an expected value given the observed values, given the x's, and given whatever the current value of the parameters is. So this is assuming I'm in the middle of the iterations. So if I think about that, the key thing here is to think about which of these things are random in terms of what I'm taking expectation with respect to. Since I'm conditioning on the x's, those are not random. Those are just constants. And the parameters are just parameters, so those are not random either. So the only thing in here that's random are the z's. So when I take an expected value, I'm basically thinking the only thing that's random in here is the z's. Ideally, those would enter in a linear way, and it would be easy to take this expected value. In other cases, we might end up with, like I think in the problem you're working on for the problem set, you're going to have some z squareds and some z's, and you're going to have to take expected values of z squareds and expected values of z. In this case, if I look at this, I notice that, well, these are summations, so I can pass the expectation inside the summations. And if I do that, I'm going to get something that looks like the sum over I, sum over k, the expected value of the indicator that zi equals k. And nothing in here is random in terms of this conditional expectation I'm taking, and nothing in here is random either. So those things just get passed through the expectation. So then I just have the fk times xi given mu k sigma k, and I have plus my log of pi k. So what is this? What's the expected value of an indicator function? It's just the probability. So actually, and what I should have done, I was sloppy with my notation here, is that's a conditional expected value. So this is the expected value of this given x and given theta equals theta t. So this now becomes the probability of zi equals k given the x's, but the only relevant x for a given zi is going to be xi, and given theta equals theta t. So that's the conditional expectation. That's the conditional probability I need to figure out. All right, if I think about doing that, we've already worked with some of these distributions. We've worked with what the marginal density for z is, and we've worked with what the conditional density for x given z is. So if I think about what that is, and I think about the pieces that I've already talked about, Bayes' theorem might come to mind. So I can think about this as I'm just going to turn around the conditioning and say, this is the probability that of xi given zi equals k and theta equals theta t. So this is z given x. Bayes' theorem says I can get that as x given z times the marginal distribution for z divided by the sum over all of the values. So this is going to be, sorry, this is supposed to be z. So the marginal distribution for z is just those probabilities, the pi sub k's. So this is just the probability that zi equals k, which is just pi k. And then down here, we have a sum over k of probability of xi given zi equals k, theta equals theta t. Sorry, this is going to be the probability zi equals k given theta equals theta t. And then I have p of zi equals k given theta equals theta t. So I guess I need to wrap up here. So unfortunately, we're not. Fortunately, we're still in the middle of this. But let's see, what do I want to say about this? Well, one of the things I want to point out is, so this probability of xi given zi equals k and given theta equals theta t sort of looks like what we've already seen. This is just the normal density for x if it's coming from the kth class. But it's under the assumption, it's basically working under the condition that the parameters are the theta t's, so that instead of having the true mu k and the true sigma k, I have the current values of those guys. So this thing is going to look like a normal density for xi given mu sub kt and sigma sub kt. And similarly, this thing here is basically going to be pi sub kt. It's going to be my current. It's going to be my current guess for what pi is for the kth class. Okay. So this is where this idea comes in that I need to pay careful attention to the fact that when I'm doing these conditional expected values, when I'm calculating these conditional quantities, that I'm basically taking the parameter values to mean the current parameter values. But when I go ahead and plug all this back into here, you'll notice that everything here still involves parameters that don't have t's in them. So once I plug this back in and I start to try and maximize this, I'm going to be maximizing with respect to these guys and maximizing with respect to those guys, but where these guys are just my current values, and I'm not maximizing with respect to those. Those are just going to be numbers as I'm working my way through the iterations. Okay, so I'll pick up with that. With the derivation at that point, I'll go back and remind myself of why it is that I was confused about this guy not having this term in front of it. And basically all we're going to see next time is that if you go ahead, plug this back into here, and then maximize this, that you actually have some sort of intuitive statistical results fall out of what the estimators look like.